Well, today we're going to get serious. Serious about series. And when we talk about series, what we really mean is, hey, let's go and add up infinitely many terms together and see what we get. And you're probably thinking, infinitely many terms, that might take a while. Well, it could if we actually did it. Of course, we can't, but we can say, well, what would happen? So let's begin. So when we're talking about series, we do mean really adding up infinitely many terms. Now, the easy part is just adding up to some point and saying, okay, we'll stop here. Good. It's the dot, dot, dot. That's the hard part. Now, dot, 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 whenever we put in a dot, 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 it really is a stand-in for the and the pattern continues. So when you see a plus dot, 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 it just means and you keep going in your addition. Now, how do we add up infinitely many terms? And the answer is, well, we don't. No one's actually ever added up infinitely many terms because it would take infinitely often to actually add them all together. But what we can do is we can say, well, what would the answer be? Or maybe a better word is, what should the answer be if we were able to do it? And when you start throwing words around like would or should, you start saying, aha, limits are involved. And so what we're going to do is we're going to say, well, let's look at the pattern that emerges when we look at what we call the partial sums. So in other words, remember we said, look, the beginning, no problem. We can do that. So we want to focus on that part. We want to say, okay, let's focus on the beginning, and let's see what's happening when we add up the first however many terms. So partial terms, for example, we'll have S0 is A0, just the first term. That's 1. A0 plus A1. A0 plus A1 plus A2. And so forth and so on. So we look at these partial sums. Now they are numbers. And so we say, oh, the partial sums are forming a sequence. S0, S1, S2, S3, dot, 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 dot. Now our question is, what's happening way down there? That direction. What's at the very end? That, if there is something down there, in other words, if these converge, that's the value of the sum. So we can say, look, our sums are found by taking limits of partial sums. All right, great. So now the question, all right, what can we do? And today we want to focus on just two particular types of series where we are able to answer the question. And so we can actually say, hey, this is what it should be. And we're like, woohoo, we can do it. Now, the first one is called geometric series. Now, you might say, what does that mean? Geometric, does that mean we draw pictures? But actually, when you see words like geometric, it really means multiplication. So there's two sort of things that you often see. There's arithmetic, and that means addition. Geometric means multiplication. So when we're talking about geometric, we're saying at every stage, there's this sort of multiplying thing going on. So what we look at is we look at things of the form a r to the k. So when you have that k in that exponent, it means at every stage you're adding an extra r. So you have a times r, a times r squared, a times r cubed. And in general, a r to some power, right? And so forth and so on. Now, how do we go about adding this? Well, it's not so bad. We say, well, look, if I look at the terms, they're really not very different from one term to the next. The only difference is a single factor of r. Okay, so what can we do? Well, we look at a partial sum, say up to the nth term, and we have the first n plus 1 terms. The reason I say n plus 1 is we start at 0. And we say, well, if we multiplied by r, what happens? Well, the a becomes a times r. The ar becomes ar squared. So it's like there's this wonderful shift all the way across, and the a times r to the n becomes a times r to the n plus 1. And now I say, wow, look, they're almost identical. And in the following way, if you look at the middle block, they're exactly the same. So they agree in the middle. The only place where they disagree is at the end. So we say, well, since they agree in the middle, if we took the difference, things become really nice. So in other words, if we do our little subtraction here, what do we get? Well, we get Sn minus r times Sn. Well, that's 1 minus r times Sn. All right, that's the left-hand side. Over here, we get A, cancel, 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 right? Cancel, cancel, cancel. Do. Lots of beautiful cancellation, except this last term. Doesn't cancel. There's nothing for it to cancel with. So minus A r to the power n plus 1. So what's happened is because we have this beautiful pattern, the middle terms cancel. It's just the terms on the end that we're left with. And so instead of having a whole lot of terms, now we're down to 2 terms. So this A and this A times r to the n plus 1. So now we're saying, perfect. All right, well, as long as r is not 1, we can divide. And we end up with the conclusion, look, Sn is A minus A times r to the power n plus 1 over 1 minus r. And we're good. We've got our partial sum. And then we say, well, wait. We want to know what happens as we go to infinity. In other words, what's happening over there as we head off towards infinity? So we think, okay, well, what's changing? Where's the only place where n shows up? Well, the only place n shows up is right there in the exponent. So we can say, okay, to figure out what's happening as we head to infinity, we just have to say, well, what's happening to this term r to the power n? Now, one of the things we said is, look, if r is small, in particular, the size of it is less than 1, then when we take r to the n, it's going to shrink, go to 0. So our conclusion, when r is less than 1, our limit of our partial sums, which is telling us what our sum should be, which is the limit of this expression, a minus a to the power times r to the power n plus 1, or 1 minus r, becomes a over 1 minus r. In other words, this one piece which has the n goes to 0, and life is good. So we have the following. We now know how to sum a geometric series. And in general, we say, look, as long as what you're multiplying by at each stage is below 1, then a times r to a power, the sum of it is a over 1 minus r. Now, the way I like to remember this, and you have to be a little bit careful here, you really have to make sure you have it in the right form. So what's the key? The key to a geometric series is at every stage you multiply by r. So that's how you know if you have a geometric series. Do you say, look, do I multiply by r at every stage? And if the answer is yes, then it's geometric. Where does the formula come from? Well, the a, you should think of this a is your first term. So in other words, it's where you're starting. See how we start with a? The r, this piece here, this is what we have we can call it our multiplying factor. It's what you multiply by at every single step as we go from term to term. So once you recognize, oh, this is a geometric series because at every stage I'm multiplying by the same amount, then you say, okay, well, what's your first term? What are you multiplying by at each stage? And now you have that expression, a over 1 minus r. Now, the reason I say be careful is we can do things where maybe we don't start at 0, maybe we start at 2. You're like, does that not work? No, it still works. You just have to think, what's my first term? What am I multiplying by? And then you have the formula. So just remember, first term divided by 1 minus your multiplying factor, and life is good. And of course life is good. It's wonderful. We're doing calculus. All right. Now, as a word of warning, you have to have r be small. You might say, oh, wait, there's nothing about a over 1 minus r that doesn't say, look, what if r is 2? Doesn't that work? No. This is the thing that gets tricky with infinity, right? You might say, well, if r is 2, I could have 1 over 1 minus 2, which is negative 1. It feels like, what is that saying? That 1 plus 2 plus 2 squared plus 2 to the fourth equals negative 1? The answer is no. It doesn't work. And the reason it doesn't work is that this assumption here, this formula, relied on the fact that this term went to 0. So just be careful. Sometimes you say, oh, there's this nice formula here, and you say, okay, well, it works for all choices. No. You got to remember, it has to be small. The size of r has to be below 1. If size of r is above 1, forget it. That means that the terms are getting huge. No chance. No chance. All right, so that's geometric. And what was the theme? Well, the theme said, well, by looking at the partial sums and just sort of doing a slight, see what you were doing, what you can think of is a shift and the cancellation. That's what happened, right? We multiplied by r to get a shift, subtracted to get cancellation in the middle, so we just had the terms on the end. Well, we want to sort of explore that idea of, hey, cancellation in the middle, we like that, let's do some more. So this is what we call telescoping sums, or we could have telescoping series. So the nice thing is we like things to cancel. Now, you might think telescoping seems kind of a weird phrase. To help you visualize what's going on, you can imagine that you're watching like one of those old pirate movies where they have the telescopes, right? Where you could pull it out, or you can push it in, right? You have these telescopes that would collapse. And so we want to have that sort of same flavor going on. So what a telescoping sum, or a telescoping series, says is, hey, you're going to get cancellation going. Now, what do these look like? Well, they have the form of, there's some function, that should be an equal sign there. There's some function, f of k, and you subtract f, k plus l. So, in other words, there's some function out there, and your individual terms look like the difference of it offset. So, let's spell it out a little bit more for at least a special case, right? So, suppose you had the sum, we'll do k equals 1 to infinity of f of k minus f of k plus 1. What would this look like? Well, it would look like f of 1 minus f of 2. That's the first term. Then plus f of 2 minus f of 3. That's the second term. Plus f of 3 minus f of 4. That's the next term. Plus f of 4 minus f of 5. That's the next term. And of course, dot, dot, dot. And what happens, you say, perfect. What do you see? Well, we say, look, these terms cancel, and these terms cancel, and these terms cancel. And so it feels like, whoa, all the terms are canceling except the term at the very start. And so that must be our answer, right? Well, maybe. Let's back up. Now, the idea of cancellation, that's the key thing here, is you get cancellation. Why is it maybe not just the first term? What you have to remember is we're really thinking of partial sums, right? So if we think of a partial sum, what would happen if we look at S, say, n, then you'd say, look, well, what you'd have is you'd have the first term didn't cancel, and then to go, and then the very end wouldn't cancel. So you have minus something like f of n plus 1. And now you say, okay, so here's the key, is that in the partial sums, you're getting cancellation except at the very start and at the very end. Now the question says, look, the start is fixed. The end, we're drifting off to infinity. So what you care about is what's happening to this part. What's the behavior? So for instance, if it's going to 0, well, that means that this part goes away. You're just left with the first term. Life is good. So that's what this bullet point is. If this function is going to 0, then you only have to look at the first term or first few terms. Now you might say, why first few? Well, it depends on the offset. See, this is an offset of 1, which means, look, you get cancellation right away. But I could offset by 3, which says, look, the cancellation here happens 3 steps down. And so you have to sort of pay attention. It doesn't necessarily mean exactly offset by 1. You might have to go a couple of terms. If this value heads off to infinity, or maybe it doesn't converge, then okay, then the sum either goes to infinity or it doesn't converge. I mean, all sorts of things could happen. Now, the tricky part, and it's maybe not tricky, but it can be subtle, says, well, hold on, what if it actually converged? So maybe fn goes to some value. What then? Well, that's perfectly fine. We say, no problem. Then what we have to do is we say, look, the first term is what it is. It's, f of 1. The last term, it goes to c. And then we say, all right, perfect. So we can still do it, but we pay attention. So the whole idea of telescoping sums is to say you get cancellation in the middle. So you have a couple of terms at the start, depending upon how much you offset. And when I talk about offset, it's that plus L. And then you get a couple of terms at the end. And now you say, well, what happens to the terms on the end? That determines whether it converges, and if it does, you combine what happens with the start and what happens at the end to get your answer. And again, it's this nice idea of cancellation. So cancellation is a wonderful thing when you're trying to figure out what the values are, because cancellation says, hey, you've got a lot of zeros, and if it's one thing we like to add, we like to add 0. It's really quite nice. And so, yay for 0. Yay for 0. All right, well, those are our 2 sums that we can do, geometric sums and telescoping sums. Now, there will be some other sums that we talk about later on. But as a general rule of thumb, whenever you see a problem that says, find the exact value of a particular sum, there's only a couple things that can happen. One, it could be infinity because it's just getting so huge, and that's the answer, right? It could diverge to infinity. But usually it means that it's geometric, because we know how to find geometric, or it's telescoping. The other thing it could mean is that there's something called the Taylor series, which is what we're going to build up to, and that's several sessions down the road. So for right now, we're really going to be focusing on geometric and Taylor. I suppose the one thing I should really emphasize is sometimes it's easy to spot a telescoping sum, sometimes it's a little bit more subtle. So what's the key? A telescoping sum is anything that you can rewrite in the form where you have a function and a function that's been offset. But it might not start out in that way. So an example, well, look at 1 over n squared plus n, and you want to add that. That doesn't look like telescoping at all. But here's the thing. We could think of this as the sum of, and I should add some bounds here, so we'll start from 1 to infinity, 1 to infinity. We can think of it as 1 over n times n plus 1. And you're like, yeah, Steve, it's the same thing. Of course we can think of it that way. But suppose it wasn't a sum. Suppose it was an integral. Because really at the heart, summation and integration are connected together. They're about adding things up. Okay, if you had an integral where you had 1 over x times x plus 1, what would you do? Partial fractions, right? Yeah, you would. Come on, you know you would. So here's the thing. If you do partial fractions, and I'll skip the details, what would you end up with? Well, you'd end up with the sum 1 to infinity of a half over n, 1 over n minus 1 over n plus 1. That's the danger of trying to do things in your head. Okay, that's what it would become. And now notice, you say, aha, this is like f of n plus 1. So it's the function 1 over x, and the offset is by 1. And so it's of the right form, where it's like, oh, these are the same expression, just there's an offset, n plus something. And when you see that, that says, oh, there's going to be some cancellation going on, and life is good. All right, well, time to go do some practice. See you soon.